cleaning.
Start on this side.
Right, it will dry by the time.
Yep.
Just wait a minute for this to get done.
Sure,
So
no problem.
Give you that back on the other end.
Should be dry by the time you get over there.
I have 150 minutes today, right?
150.
That's, I mean, up to a factor of 2. That's correct.
I noticed it's a little lighter than it used to be. My TASI was 4 times 90 for 4 weeks, and in
I don't
2010.
remember that.
2010?
It was 4 times 90?
I think it was 4 times 90. I might be misremembering.
3.5 times 75.
Yeah, yeah.
I mean, because our slots have been 4 times 75 for.
Oh, really? I might just be forgetting. Felt like 90.
I would be surprised, because that's a lot. You know, if you
It is a
add,
lot.
that's adding an extra hour to what we've already got.
I was the idiot that went to PITP right after TASI, and
Wait,
so
what?
yeah, it was like, whoa, overload. So
That was 2010, you said?
yeah,
That was a good
yeah. It was a great year. It was a fun year. Yeah.
Do you need to say anything? Yeah. No, I think we're good. Go for it.
Okay, welcome back, everyone. So as you know, there's a bit of a machine learning theme at TASI 2024. So last week you learned and had tutorials about kind of the nuts and bolts of machine learning. Here we're going to hear a bit of the more theoretical perspective, really putting the T in TASI. Physics4 Machine Learning by Jim Halverson, who's a professor at Northeastern University. And I don't know what those 5 letters, IAIFI, what they stand for, but something interesting. I don't know. Anyway, Jim, take it away.
I guess I can tell you, IAIFI, pronounced IFI, no one gets it right unless we tell you, is the NSF AI Institute for Artificial Intelligence and Fundamental Interactions. Can anyone who isn't affiliated with the Institute remember word for word the title that I just said? That's the NSF AI Institute for Artificial Intelligence and Fundamental Interactions, a Boston-based AI and physics institute. It's a joint collaboration between MIT, Harvard, Northeastern, and Tufts. It's wonderful. We've got something like 150. Oh, are you going to try?
I have a question. NSF doesn't start with I.
Very good. Very good. Touche. There's all sorts of reasons that the name is a little confusing. But yes, Institute for Artificial Intelligence Fundamental Interactions, IAIFI. But yes, we're wonderfully funded by the NSF, which is why it's in the name. And we're about 150 people in total. Lots of postdocs. We have wonderful IFI fellows. There is an IFI fellows competition this year. So if you hear things that you like, or you're already doing ML and you're interested in potentially joining us, please apply to our program. And I guess I don't need to say too much about the details of what we do, because you're going to be hearing a lot about it from me. You heard some of the things, even though Christoph isn't directly affiliated, you heard some of the things that he is doing is related to some of the things we're doing. You'll hear from Fiala later in the week. And if you see my enthusiasm about ML in these lectures, you should just know that sort of IFI is the physical place where that lives. Please, when you're in Boston, come join us. So that is IFI. And I have some preliminary comments I wanted to make, because sort of everyone's talking about their TASI experience. My TASI experience was as a student in 2010, and I lectured in 2017. And now it is 2024. I started my PhD in 2007. So TASI happens 3 mod 7 for me every year since my academic birth in 2007. So Oliver, please invite me again in 7 years. I would love to come back in 2031. So I am a string theorist. I work on all sorts of things. Recently, that's been a lot of ML in various contexts. Historically, there's a lot of particle physics, cosmology, and math. I work with mathematicians also that gets baked into my string theory interests. So I'm interested in all sorts of things. Last time I lectured here, I gave a lecture called Remnants of the String Landscape, which was about all sorts of things that string theory tends to give you that might be relevant for particle physics and cosmology, even though they don't solve any bottom-up problem. So the usual way of building models is not what I was talking about there. And what I talked about there has nothing to do with what I'm going to tell you about in these lectures, which is sort of some of the things that I think are important for ML. Your homework is not going to be to do any of the calculations, although you're welcome to. I have lecture notes that are going to appear in the Google Drive after each lecture, OK? And it's going to be after each lecture rather than before, because I want you to be paying attention to me instead of to the notes. But those notes are a great way after each lecture to review what I said to get ready for the next lecture. OK? I do have a question. I ask this to my students regularly when I teach. It never goes well, but I'll try it again. How many of you have heard of Father Guido Sarducci's 5-Minute University? Yes, good. Tom has. Would you like to tell us what it is?
I don't remember the specifics, but there are a bunch of pithy one-liners for different subjects.
That's right. It's pithy one-liners for different subjects, and it's an old John Belushi sketch from Saturday Night Live from the 1970s. And he plays Father Guido Sarducci, and he gets up on stage and he says, "Hi, my name's Father Guido Sarducci. I would like to welcome you to my 5-minute university. I'm going to teach you in 5 minutes what you are going to remember from college 5 years after you graduate." And it gets pretty funny, and he has these pithy one-liners. He says, "Welcome to Spanish class, ¿cómo estás? Muy bien." Next class, he says, "Business class, buy something and sell it for more." And you know, so I thought in the spirit of that, I would give you, I think part of it is because I remember from my own TASI, there's so much to learn. Oh no. It's down already, thank you. Good, OK. So maybe I can actually do it right here. There's room for this. I want to give you my version of these lectures. In ML, people love saying TLDR, which is short for too long, didn't read. I hope that these lectures you listen to carefully and also read, but in case not, I just want to make sort of 3 basic points. So CS, and you should come do it with us at IFI, is historic. We don't normally think of it in that language, because sometimes when you're a fish, you forget that you're swimming in water. There is this wonderful book that I read about 7 years ago when I started doing this line of work by Walter Isaacson, the guy that wrote the Einstein biography and the Jobs biography and so forth. It's called The Innovators. And in The Innovators, he sort of goes through the history of computer science, highlighting all these awesome things that have happened. But of course, it starts in like 1800 with Babbage and Lovelace. And then there's like a lull. And then it's Turing and friends cracking the Enigma code. And then it's computers the size of a room in the 60s. And then the PC happens in the 70s and 80s. And when I was a kid, the internet came into existence. I remember 1994 very vividly. But the point is that we're sort of living, historically speaking, at the beginning of computer science. We're pretty close to the beginning from the point of view of like our distant descendants. And I think that that is something at least that inspires me, and hopefully it inspires you. So I think we should keep that in mind, that what's happening in computer science is really revolutionary. And I think that it is going to affect science and scientific discovery in very important ways. The second part of my TLDR is that machine learning is now. It might happen in the future also, but it will happen in the future also, I think. But something has been happening in machine learning in the last 10 years, which is why you have discussions at Thanksgiving dinner and things like that about it. You know, everything from basic image classification 10 years ago that was GPU accelerated, through the stuff that got me hooked, which I'm a chess player, the chess-related stuff and the Go-related stuff in 2016. It is generating images that really could fake you out, and you know, people that don't exist that you would be convinced do exist. Large language models, GPT, the whole thing, it's really happening now. And I think, you know, I'm running out of room, so I'll just ask the questions rather than writing them on the board. One of the questions that I think hasn't been answered and won't be for a while in machine learning is to ask, what is it like in other areas of science? So I used to think, and I still think this is true in certain contexts, that it's just like hadron physics in the early 60s. Tons of data, lots to explain, and we just need to come up with QCD, OK? That, I think, and I hope, is going to be true, and I think it will be true in some contexts. On the other end of the spectrum, it could be that ML is like sociology, and that it's emergent and important, and there's, you know, things that can be said and studied, but we don't try to do sociology mechanistically and in terms of models quite the way that we do with physics. That's the other end of the spectrum. And somewhere in between, maybe you think about biophysics and our friends that have mechanisms for various effects in biophysics. And I think different things in ML are going to be like different corners of that spectrum. Sometimes it's going to be like hadron physics, and we just need to come up with QCD. Other times it's going to be beyond our ability to come up with mechanistic models. And sometimes it might be in between. So whatever the case is, ML theory contains but is not equal to understanding neural networks. Is the size OK? Larger? Good? Good. You are exactly the people that I want thumbs up from, all the way in the other corner. So that's how I'm thinking about it. I am hoping that we can come up with the types of understanding that we're used to in physics to try to understand what's happening in machine learning. We should be building models. We should be mechanistic about it. We should have a theory. And whatever that theory is, and I think there's a lot of things, it has to include understanding neural networks. And this is what the topic of these lectures is. And of course, I invite you to interrupt me at any time. OK. Where am I? Good. So what I'm going to do today is I'm going to give you a little bit of an introduction that sets up how I think about this problem. And it's all going to be in the context of understanding neural networks. My proceedings notes, that level of notes, will almost certainly have things beyond understanding neural networks. But I'm going to focus these lectures on understanding neural networks. So I'm going to give you some introduction that is my way of thinking about this problem, and others too. And there's going to be 3 pillars that come out of it. And we're going to focus on one of the pillars today. And I've left it blank so that I'll fill it in. We'll ask a central question, and I'll tell you what the pillars are. So I'm going to start, as I talk about neural networks, with the following question. Actually, not a question, just to tell you some sort of definitions. Neural networks. So a neural network is a function phi sub theta from RD to R. And some of you are probably already complaining. I don't just want real valued neural networks. Yeah. I'm someone who appreciates the Sidney Coleman school of learning quantum field theory, where you really learn scalars to death and learn renormalization deeply, and that many of the essential aspects of quantum field theory are already there for scalars, and you should also think about fermions and gauge fields after that. But scalars already have a lot of meat. So we're going to take a Coleman-esque approach to ML here, where we're going to do scalar neural networks. So we spend a lot of our time in physics sticking indices on things. Of course, you can stick indices on the neural network and have it be a vector output or a tensor output or something like that. But in most of these lectures, the neural networks are going to be scalar. I need to give you some lingo. So the input to the neural network is a point in RD. And if you want, you can take that point in RD and reshape it into an image with pixels if you want. The output of the neural network is going to be phi theta of x in R. This is just establishing some language. The network itself is phi theta, which lives in the space of maps from RD to R. Some of you with math backgrounds are already saying, what sort of maps? How differentiable should they be? And we'll sort of take a physicists and CS approach and say differentiable enough to be useful. There's a very famous thing called a ReLU activation function. It's not differentiable. It has a kink. So the function is literally not a differentiable thing. But in practice, you never encounter that non-differentiability because it's non-differentiable at one point, and you're feeding real data through it, and it never hits it. So differentiable enough in the space of maps. And finally, we'll have data D. OK? So there's our data D. We have inputs that live in RD, outputs that live in R. The actual neural network itself is in the space of maps from RD to R. And our data, this is going to be some script D. That's supposed to be a script. And one thing that I forgot to say is that this neural network has parameters. So it's a parametrized function. OK. Very good. Cool? OK. Actually, I need this now, because this is sort of the central question of the lectures. What does a neural network predict? I know you already had neural networks with Christoph, so I know you have some experience with them. They have parameters in them. And for a fixed value of the parameters, you feed in an input, x, and what it predicts is the output. And so like, there's a dumb version of the answer to this question, which is that it depends on, it's just phi theta of x. That's what it predicts. But part of the problem is that there's some caveats associated with that, which is that the network has both statistics and dynamics. And so the predictions have some sort of statistical property and some sort of dynamical property. So yes, it predicts phi theta of x, but we need to talk about these caveats in detail. So the first complication is dynamics. OK? So in ML, what we have is trajectories. That is not how you spell trajectories. And we have a couple different types of trajectories. We have trajectories in parameter space. And so this theta, the parameters of the neural network, is really theta of t. And it lives in some r to the magnitude of theta. I'm taking real parameters here. So as the neural network evolves, you can think of the initial point in parameter space as sweeping out some trajectory in parameter space. There is an associated output space trajectory. And that's that phi theta of t of x lives in R. So there's some trajectory through R. And there's also some sort of function space trajectory. And so phi theta of t gives you some trajectory in the space of maps. Okay. Cool. So you kind of know this. Neural networks are trained. That's why NVIDIA's stock prices are up so high, because they make GPUs that are really good at making this dynamics happen quickly. But let me give you an example. So in a supervised setting, this is called supervised learning. I have a setup like this. The supervised dynamics has a data set D that's a set of inputs and outputs in RD times R. And if you find yourself furiously writing, remember I'm going to give you these notes at the end. So I have this data set. These are the inputs. These are the outputs. They come in pairs, because you feed an image of a dog, and the label is dog, not cat. Okay. And a loss function. So the loss function is a functional that depends on phi of theta. I'll take it as a sum over the data of an element-wise loss. Sorry, this should be alpha. Okay. And given such a loss function, you need some way, so at one given slice in time, the neural network might make terrible predictions, and the loss tells you just how terrible they are. And you need some way to update the network that induces the trajectory in parameter space. And here, a simple example is just to take the gradient of the loss function with respect to theta I, and to just follow this loss function downhill. And this, of course, is gradient descent. OK. OK, so like this is called Physics4ML. Generally, I'm going to try to take a 4ML posture in these lectures, even though my mind is very for physics. But you know, this is like a ball rolls downhill, gradient descent. Yes?
Can we say that the function space is changing given that we have changed the parameter space?
I would like to think of there being, yes, thank you. The question is, can you think of the function space as changing? I would like to think of a movement. At every point in parameter space, I have a map into the space of functions. And a trajectory through parameter space is just determining a trajectory through function space via that map from parameters to functions. So I think of it as a fixed function space. Yes.
Yeah, last week we introduced stochastic
Yes.
data. I think we just have to say that the data that we are supervising.
You want to know what SGD is?
Well, yeah, we did that.
Cool. Good. So you did SGD last week.
Yeah.
Yes. Very good.
But I'm asking, like, here you're not talking about stochastics.
Good. Yeah. So the loss here is a sum over the data. So there's something called full batch gradient descent, which we will theoretically work with in a setting in a day or two. Full batch is where you say all of the data gets trained on every epoch. Stochastic gradient descent says I'm going to take my data and I'm going to train on some subset of the data every epoch, and it's going to be a different subset. So I'm going to randomly draw data from the full set of data, and I'm going to train on that each epoch. So that's where the stochasticity comes in. It's not a sum over all the data. It's a sum over a subset called a mini batch. Good. Anyone else? The interruptions are useful. OK, good. Very good. Where was I? OK, so that's the basic setup. Yes?
About the D data. So does that constitute the? Or, okay, never mind.
D theta?
I figured it out.
OK, great.
I was wondering whether D includes the weights or the parameters of the function, but it looks like it doesn't.
What is, no, D's just the data. The parameters are these thetas. And the point is that the data, the network predictions on the data come into the loss and update the network and the parameters through gradient descent or some other algorithm. Yep. Good. OK. So the question was, what does a neural network predict? Phi theta of x, that's what it predicts. But it's complicated by dynamics because the thetas change in time. It's also complicated by statistics. Good. All right, I'm getting used to these boards. Thank you for your patience. So it's complicated by statistics because when you start your computer, and when you did last week in your IPython notebooks, you had some initial value of the parameters, theta, that were drawn from some distribution on parameters p of theta. OK? And if you were to restart your computer, and you haven't set the seed, then it'll be a different draw next time around and a different draw the time after that. So you have all of these different points in parameter space that your neural network starts at, which gives you different points in function space that your neural network starts at. And the point is that that's just not fundamental. That's like to the whim of some random draw. And if we're trying to understand neural networks, we had better maybe do a little better on that point. OK? So the prediction. Good. So good. Phi theta of x is not fundamental because theta is drawn randomly at initialization. What we should really talk about is the expectation value over the thetas, which is the expectation value over the thetas at initialization. OK? And this expectation is, of course, just the integral d theta p theta phi theta of x. Now I'm talking about something fundamental because, yes, any one draw of the neural network at initialization gives me one particular random function, but I can compute the average prediction. This is the average prediction over all of the initializations. Yes? Of what? Yes, sorry. This is the that's very expectation value over theta. Theta drawn from p theta at initialization. And it's realized by this integral.
You said that the average was the same as the average for the initialization, but isn't the theta going to change over time? Isn't that the whole point of making a machine learn?
Patience. Wait 2 minutes, OK? Very good. Yes, so at initialization, I'm still at initialization here. And you could compute the average prediction. You could also compute the average product of the predictions, also known as a 2-point function. Good. And so this is plus higher moments. Good. I should also say plus higher moments. So this is the average prediction and the average product of predictions are just the 1-point function and the 2-point function. of the neural networks at initialization. And so this information all is relevant to the problem. I'd like to put it in our language. OK. Oh, sorry. And throughout, I'm done writing E of stuff. I'm going to be a civilized physicist, and E of dot is henceforth bracket of dot. Okay. Bracket of dot. Bracket of dot means statistical expectation value throughout. Bother me about the word quantum later on, OK? I will have answers for you. But for quite some time until the end of the lectures, this means expectation value over some distribution of neural networks. But bras and kets are also easier to write. So my notes have tons of bras and kets in them. And we want to put this average prediction in our language.
Jim, there's another question over here.
Yes.
Do you have like really weird homological P of thetas where you can still sample from P of theta but not compute these expectation values or higher moments?
Good, maybe. So the question is, can you have weird P of thetas? Yes, because you get to choose P of theta. You put a conditional on it. Can I have a weird P of theta that I can sample from but still not compute these expectation values? I guess if I can sample from it, I can still estimate the expectation values via Monte Carlo. I don't see what goes wrong.
Those blow up or something.
Yeah, they could diverge. Yeah, good. So it could be that no number of samples would give rise to a convergent correlator. That can happen, but in many cases it doesn't. Yes.
A more basic question: what do you mean with higher moments?
Yeah, good. So this is the first moment because it's the expectation value of phi to the 1. This is the expectation value of phi squared with x's and y's inserted. The nth moment would be the expectation value of phi of x1 through phi of xn, which, as I was sort of alluding to in our language, this is a 1-point correlation function, this average prediction. This thing is a 2-point function. And your question was about higher moments. The nth moment is the n-point correlation function. Okay. And yeah, that's the setup. OK, so the point is that yes, there's dynamics, and yes, there's statistics. At initialization, no one neural network is fundamental. And so we should really talk about the average prediction and the average product of predictions and so forth. But those are just correlation functions. OK? Yes?
So with the, if we later are sampling from the distribution at a time, it'll be because the brackets don't tell us what training time we're averaging at. How would you fit that in?
Yeah, it's the same answer to the question you asked a minute ago, which is that it's coming in like 10 seconds.
Okay, and
yes.
Also for the multi-point correlations, which is instead of putting x and y, could you just write x1, x2, so we don't confuse y for the network output of
good. So I can probably change that in my notes, but because it's in my notes as y, I'll be a little coy about that now. So please keep track of whether y is an input in the context of a 2-point function like this, or it's a label. But yeah, that would be better notation. So DM me on Slack about that, and I can change the convention in the notes. Very good. And the question that you keep asking is that really there's dynamics and statistics, not just one or the other. Okay. And the dynamics and statistics in particular, so if you'd like, this sampling over here I was thinking at initialization. So it's at some initialization distribution. But at time t, you can think of theta at time t as being sampled from some distribution of parameters at time t. So we talked about how this dynamics introduces a trajectory through parameter space. But really, when you think about that, for every sample, there would be a trajectory. So the distribution actually has a trajectory also. And that's p theta of t. And in that context, you could talk about what I call here gt1 of x, which is phi theta of x evaluated at time t in the p theta of t distribution. Similarly, sorry for the y. It's a very valid complaint. Okay. Similarly, you could do this, that regardless of whether we can compute these things, these are fundamental objects to track. The average prediction of the neural network and the average, this is related to the variance of the neural network predictions as training happens. Okay? And so in particular, one thing you might be after, you might want g1 infinity of x. And in English, g1 infinity of x would be the mean prediction of an infinite number of neural networks trained to infinite time, which presumably in infinite time it'll converge. Okay. Now, I'm trying to set up some sort of theoretical edifice here. One thing that's amazing is that there is a result from the machine learning theory literature from 2018, 19, 2020-ish, that in a particular limit in a toy model, there are caveats, and we'll talk about that, you can actually predict that thing analytically exactly. It is an exact equation for the mean prediction of an infinite number of infinitely wide neural networks trained to infinite time. Okay. So even though this sounds absurd, like I'm stating the thing that I want, even if it's hard to get in general, and in a particular toy model, you can get it. Okay. But on fundamental grounds, knowing, since the initializations aren't fundamental, knowing what your neural networks, what the full ensemble of neural networks is going to predict on average as you train to convergence is a fundamental question. Okay. Good. There's
I have a question.
Yes.
I noticed that this G1 infinity, it doesn't depend on the entire data set you give it.
It does, because I haven't told you how I train it here. I'm just saying that however I train it, the training is going to affect the drift in the distribution on parameters as a function of time. This is a very general setup. In supervised learning, that would quite literally happen. And the data would affect the prediction through that.
So this G1 infinity is a function of the data.
Yeah, it's an implicit function of the data, because how P of theta evolves in time is a function of the data. Yeah. So I'm trying to give you a very general framework. I'm trying to put the T in Tassie, I guess. I don't know. But OK, so I have two of my pillars. Good. I'm going in the order that I'll present them in. Statistics and dynamics. OK? So there's one pillar clearly missing, and I'll make it in a point. I'll give you an example, and I'll let you complain. Consider phi theta of x, here comes an architecture, equals theta dot x. Now, someone complain. I could do this whole statistics and dynamics story with that example. Why shouldn't I do this?
Make theta the, or never mind. I was just going to try to say, oh yeah, this is the quantum mechanics, Schrödinger equations that can solve anything in existence.
I'm not quantum, yeah. I'm not quantum yet in these lectures. And in fact, I won't be quantum in these lectures. Does anyone want to complain about this neural network architecture, theta.x? Yes, Sean.
You've made linear regression, which is awesome.
OK, good. Linear regression is awesome for some problems, but for other problems, linear regression is terrible. So that's exactly the point, that this is linear regression. And for some models, it's great. But for other models, we say, in general, the lingo that I actually have grown to love over time, it is not expressive enough. So this architecture, though for linear data, this architecture is very good, for general data, it's not expressive enough. Okay? So the question that you might ask here associated with expressivity is how powerful is a neural network? Which is roughly the question, can it approximate anything I want? Because if I give it a general learning problem, I might want to choose an architecture that is expressive enough that it can handle basically anything I throw at it. Okay, in principle. So that's the third pillar.
So what happens when you take this linear regression? What does it do that isn't expressive?
Yeah, good. So that is for all times t when you train it, there will be some theta of t. And for those values of theta, this makes predictions for every x in the domain. And it's just linear. And what that means in particular, if the labels are not linear, then this is going to make bad predictions. Because the model's not expressive enough. Linear regression doesn't apply to every model, to every data setting. Yes? Yeah. Yeah, in certain cases, it converges to a Gaussian density on functions with known mean and covariance. So it's convergent. Oh, sorry. You mean whether I can get to convergence in time?
The question basically is, in which cases it converges and in which cases it doesn't?
That is highly dependent on the choice of architecture and the parameter distribution. But there's known cases in which it converges. And to re-emphasize the point, I can do this computation analytically without ever turning on a computer, in principle. You do it on a computer in practice, but, no one is putting an infinitely wide neural network on a computer and training it to infinite time. It's that there's a different duality frame that opens up, and there's a different description of the system, and you can solve it. That's a great question. Thank you. Good. Very good. I'm almost to a point which would be a good point for a couple more questions. But maybe I will just tell you about these pillars here, because we've got them now. So the linear model is not expressive enough for general problems. So I'm going to organize my lectures according to expressivity, which is the question of how powerful is the neural network. Statistics, which is about how do I characterize the statistics of the ensemble of neural networks. And dynamics, which is about how do I track time evolution. Are there toy models where I can do it exactly? Do those toy models have drawbacks? And if those toy models do have drawbacks, what should I do differently? So that's sort of the outline of the lectures. We're going to do this as physicists. So maybe I should say what that means. I was told Physics4ML. So a couple things that you already saw up here are notions of field theory. I won't say too much about landscape dynamics, but this loss function is on billions of parameters. And it's some very non-convex loss landscape that is similar to what happens in cosmological models with many scalar fields, which string theory gives rise to, which is why my brain works that way. But it's similar to protein folding. It's similar to spin glasses. Lots of places in science, there are energy landscapes with many metastable minima. And finally, something that I will say something about is symmetries. Another thing about what it means to be a physicist is to have the right balance of rigor and intuition. So I told you this neural network lived in the space of maps, and I gave you the glib answer that it's differentiable enough, because I don't need more than that. I just need it to be differentiable enough so that whatever learning algorithm I have, it can backprop and update. We're not going to be concerned with proofs. We're going to be concerned with understanding order 1 phenomena, because what's happening in machine learning is that there's a million things to understand, and we need a sort of a phenomenology of machine learning to try to understand from a couple of different angles how do we put the pieces together and understand it. And at this point, in my opinion, generally speaking, rigorous proofs are not the direction for progress. Putting together the pieces from a couple different angles and understanding what's happening is the way to make progress. So Physics4ML is topics like this, but it's also the fact that we're going to balance mechanisms, which we want, against, maybe we don't always need to prove things. Okay? Cool. That's my introduction. That's just part 1. I have 35 minutes left, which is actually OK, because this thing here is expressivity. I'm going to tell you about the universal approximation theorem and the Kolmogorov-Arnold, I'm working on this, Kolmogorov-Arnold representation theorem. But are there questions at this point? You can take questions for 5 or 10 minutes and still get where I want. Yep.
So suppose I don't converge exactly, but I oscillate about a minimum with some characteristic frequency, then...
You mean that the predictions of the time-converged ones have variance?
Right.
Yes.
Right. Then
okay.
Is it useful useful to use a sort of thermal description?
Maybe? I haven't thought about that. That's good. The question was trying to sort of think of it thermodynamically. The way that I think about it, which arises in that specific context, is that there's a mean prediction that can be computed. There is a two-point function that when you subtract off the product of the means, it gives you the variance, right? It gives you the covariance in particular. But actually, in those setups, the theory is Gaussian. So all of the higher moments are determined by the one-point function and two-point function. So I don't think of it thermodynamically, but the spirit of what you're saying is to try to characterize the fluctuations. Because if you're, I don't know, if you're doing jet tagging in ML for jets or something, and you retrain your neural network and it makes different predictions, you might want to be able to characterize the variance of the predictions. So I don't think of it thermodynamically, but certainly we wish to characterize the statistics and the covariance. Anyone else? Right speed, too basic? Faster? All right. I'll give it one more second while I take a sip of water if there's more questions. No? Yes, good, thank you. That's why I wait. Yeah. Yeah. Sure.
What is the difference between the input and the data?
And the data? Good. The input, I'm thinking of this as a function. The input is just like the thing that goes into the function. The data may have more than just the input. So for example, in the example I gave, the data also has labels. So every input has a label associated to it. So it might be an image of a dog, and the label would be dog, but the network might predict cat. And you would be trying to train the network to predict dog. So the data can be quite complicated. There's all sorts of different data that can arise in machine learning. But because a neural network's a function, it always has an input, which lives in some domain, and it always has an output that lives in some codomain. Does that help?
So is it sort of like extra parameters?
No, the data, the parameters are like literally numbers that appear in the neural network. The silly example I gave, the thetas are the parameters. The data is, LHC data, Astro data, dogs and cats, text data, whatever it may be, whatever data you're trying to do, industry or science.
It looks like this is data up here, right, in the upper right-hand corner.
This yeah, that D up there is an example of data.
An ordered list of inputs and their corresponding outputs.
Yeah, this isn't.
With an index.
This data is data in the context of something called supervised learning that always has inputs and outputs. It has labels associated with it. But there's other ways that depending on the problem, you might set up the data. Yeah?
Maybe you're going to talk about this, but which loss function are we going to use?
Good. You can choose anything. So last week you did variational inference. So you heard about maximizing the elbow to minimize the KL divergence. That's one you could choose. In cat and pardon?
Something specific for this purpose.
I'm speaking of it very generally to just keep doing as much theory as I can without specifying the problem. In one case, we'll use mean square error loss, which you know very well. For classification problems, you typically want to use cross-entropy type losses to do classification of images. So the loss depends on the setting. The data depends on the setting. But the thing that's sort of constant is that there's a function called a neural network that has inputs, because it's a function, and it has outputs, and it has parameters.
I was just imagining that because we are talking about QFT here, or trying to be like relate with this, maybe we are talking about a specific loss function.
No, not yet. Not yet. And in particular, I mean, these correlators that I emphasized are natural to the theory. They happen at initialization, but they also follow through in time as theta of t updates and the distribution of parameters updates. But how it updates depends entirely on the problem. And I mean, what I'm doing is building up a very robust setting for talking about it generally. And then in some particular context, you could choose a loss function. You could choose an architecture. You could choose the data and try to run the program. Yeah?
Can you say anything about the nature of the dynamics? Like, you're talking about like ball going down the hill,
Yeah.
which would then some kind of Hamiltonian, and then you have like the entropy stay constant over time, but you kind of want the probability distribution to squeeze towards the right-hand side.
Good. I think maybe what I'll say is that this is just normal gradient descent, but there is recent work to do something called energy conserving descent, which basically it's by Bruno De Luca and Eva Silverstein. And they basically have a setting where they're doing Hamiltonian dynamics with energy conservation, and they're using this very physics-motivated optimization algorithm. D theta by dt has a different form in that setup. It's some different dynamics to optimize in theta space. And this is a whole field in machine learning, how to optimize the parameters. A famous algorithm called Atom from 2014. I don't know, it's got like 200,000 citations or something. So this is an entire, the general thing is d theta I by dt equals something. And there's a whole field that deals with this something. And this ball rolling down the hill is only the very simplest version of it. It's a great question. There was one in the back, yeah.
Yeah, because you mentioned cats and dogs.
Yeah.
In that case, the input is the image. What is an image?
The input is the image. The output is the correct label of whether it's a cat or a dog. And the neural network could misclassify it and say that a dog is a cat or a cat is a dog. Yeah.
But the inputs are very specific. The space of all pixels is very larger than images.
So say it one more time. The space of all.
Space of all pixels,
Yeah.
all kinds of images you can have. So kind of images
Good. So pixel space, since you raised it, let me consider an n by n image. Can I be grayscale for simplicity? So grayscale goes from 0 to 255, right? So the input space grayscale images look like, good, r to the 250, sorry. Yeah, it's just z actually. Sorry, it's 0, this is what it is, 255. To the n by n for an n by n image. Because you have a choice of 0 to 255 for each one of the n by n pixels. But this is just some shape, and all of the real numbers here happen to live between 0 and 255. And if you want, you can reshape that into a vector in Rn, in Rd. So that's what I mean when I say the data can have shape and be like an image, but you could collapse it and flatten it into a vector. And so I'm using this as a framework for thinking generally about the setup. Oh, that's true.
So we only care about networks prediction on images which have a cat or dog.
For cat and dog classifications, that's what you care about. But I forget how many class labels ImageNet has. Does anyone remember? There's this famous problem from 2012 that was like one of the breakthroughs in ML that made people start really paying attention. Thousands of class labels? I don't know. But it's not just cats and dogs, which is 2 class labels. It has many, many, many. So it can do hats and houses and so forth. Oh, yes, that's a great question. Sorry, we're getting a little bit astray, but I'll answer it because it's the question was, the space of all images is way bigger than the space of images of cats and dogs, right? So, but GPT is really good at generating images of cats and dogs. It's not quite doing this, but here's how to think about it. If I have n by n grayscale images, that's the space, right? Some subset of those to you are going to look like a cat or a dog or an apple or whatever. But if you draw those pixels from a uniform distribution on 0 to 255, it's just going to look like noise, right? So uniform draws on that space look like noise. And then the question is, can you have a neural network that learns how to sample from some distribution that is localized on images that look like cats and dogs? And that's exactly what these generative models do. They're modeling the density on the full space of images. They don't want it to be uniform. They want it to be peaked on things that look like data. And that's...
My question was really that directs you put in the 1-point function or the 2-point function.
Yeah.
Should it really be space of all images, or should it be
Sorry, the image thing is just one example. I'm just making the point that whether it's cats and dogs or jets or just some function or a Calabi-Yau metric, the network is a function. And functions have domains, and those domains get fed into the function, and it spits out something else. Yes? I think I don't understand the question.
So I can think, like, say, just the LHC, that
Yeah.
never appear ever in nature.
Yes.
And so they don't appear in my training data set.
Yes.
Your neural network will make a prediction.
Oh, that's true. I'm sorry.
How am I supposed to think about that?
Was that the question about things that are outside? OK, good.
You don't care about things that are not anything else.
Yeah. In a data set, there's the data that you train on, but then you also want your neural network to make good predictions on things that it hasn't seen during training. So it needs to be good at classifying images that it hasn't seen before. And so that's something called test data and making good test predictions. And one of the reasons why ML theory is not just neural network theory is that that's something called generalization. Why are our models good at extrapolating beyond the data that they've seen, even data that might be drawn from a different data distribution? Am I getting close to your question? Yeah. OK, great. My point throughout is not any one specific data set. It's just to say that neural networks are functions that have inputs. When you train it, you're training it on some actual data set, but your network still makes predictions on things that it has not seen. And a good network is one that makes good predictions on things that it hasn't seen. So it can label dogs, even dogs that it hasn't seen before.
Oh, I think what the point is.
Yeah.
So,
This is, and then I'm going to stop it because this is very far afield. Yeah.
I think the point you're making is that you train a network on images like cat and dog.
Yeah.
But we could fit in an image of a balloon, for example.
Yeah.
But then, is that what?
Yeah, maybe just a garbage which 0 and 1 is alternating.
It will still make, so if the image lives in the domain of the function, the network will still make predictions, and it may or may not make sense to talk about those predictions.
Yeah, so I was just saying we don't care about its prediction on the garbage.
Yeah. Yeah, that's. Oh, that's true. Yeah. Yeah. Yeah, that's true. It's a good question. But it's a domain, and the data that it trains on are points in the domain. Some of those are images of dogs. Some of them are just noise. Some of them are images of balloons. And balloons and noise are outside of the training data. And it will still make predictions. And indeed, you have to worry about adversarial attacks. There's this famous example where you take a picture of a panda and you add a little Gaussian noise on top, and the network predicts gibbon. OK, so this is called an adversarial attack. Yeah. Good. OK. Thank you for the questions. What do I need to erase? I'll erase this. I want to give you 2 theorems. And I think I'll be able to be done at 5. So the first pillar is expressivity. And the question is, how powerful is the neural network? OK. OK. And the point is, for arbitrary problems, the linear model I wrote at the end is linear regression simply not good for arbitrary problems. So the first thing that I'll tell you about is the universal approximation theorem. And it goes like this. Goes like this. This is due to Cybenko in 1989. So f, let f from Rd to R be continuous. Then for any epsilon greater than 0, there exists a neural network of this form. Phi of x is equal to sum I equals 1 to n, sum j equals 1 to d, wi1, this is the weights of the output layer, sigma, wij of 0 xj. So I'm just writing down some architecture of something called a single layer network. These things are parameters called the biases. This is called the input weights. This is called the output weights. And this is the structure of the architecture. So I have some function. I hand you a function. And then for any epsilon 0, there exists a neural network such that, assuming that sigma is non-polynomial, that's crucial, such that the supremum, continuous on some compact set K in RD. Don't worry about the specifics of the theorem. The supremum of f of x minus phi of x is less than epsilon. OK, one more time. I hand you a function. It's some appropriately nice function. And what it's saying is that there is a neural network. For any epsilon, there is a neural network. You might have to make n rather big, such that the prediction of the neural network subtracted from the actual function itself across the entire compact set that the function is continuous on is less than epsilon. So as you make epsilon smaller and smaller and smaller, what this theorem is telling you that there exists a neural network that can approximate it. And in particular, as epsilon goes to 0, basically your neural network is exactly reproducing the function. Yes? Yes, good. There's going to be a lot of indices here. This is, x lives in RD. So this j runs from 1 to d. So that's the index in RD. This is a n by d matrix, wij, that multiplies xj. I add a d vector to it. So this is just some affine transformation that multiplies x by a matrix and shifts it by a vector. It goes through a nonlinearity sigma. And this I index goes from 1 to n. This just contracts. So what comes out of here is an n vector. And this n vector gets contracted down to a scalar by dotting into this parameter w of 1. Yes, good. These are conventions for how to label the layers. So this is the weight and bias of the 0th layer of the neural network. It goes through a nonlinear activation function. And these are the weight and bias of the first layer, which in this case, because it's a single layer network, is taking us to the output. So the reason that those superscripts are there is because in deep neural networks, you have weights and biases for as many layers as you have. And so you need these superscripts to keep track of the different weights and biases. Yes? Yes?
But if we imagine like the Rayleigh activation is just a
It can be piecewise polynomial, but not. Yeah. The question was about Rayleigh. Actually, Rayleigh is a funny case with respect to the universal approximation theorem. It is a universal approximator, but there's some subtleties that I forget. But crucially, it's piecewise polynomial. So Rayleigh is this function that goes like this and then goes like that. And so it's flat, and then it's linear, but it's piecewise polynomial. Yeah. Yeah. Yeah, this doesn't depend on the i's because I have a scalar output. Yeah. Yeah.
Yeah. So does the choice of sigma depend on your particular problem?
Yes, and I'm about to talk about one specific choice of sigma now. Yes. So there are many different sigmas for which this theorem holds, but the original proof had one specific sigma, and that nonlinear activation function gives you a sense of why this works. So why does this work? So Cybenko in 1989, he took the case that sigma is the sigmoid function. So sigma of x is equal to 1 over 1 plus e to the minus x. But what's actually coming through the network isn't just one particular x. The network sees something of the form sigma of wx plus b schematically. It's wx plus b that's coming in. And so if you look at this function in the limit, sorry, what I should really consider is sigma of wx in the limit that w goes to infinity, this function becomes a step function. Okay. But in these limits of large w, many, many step functions of different types that are getting summed together in different ways, the picture of Cybenko is that 2 steps can be a bump. So this b parameter that comes in shifts where the step is. And so you can have something like this. I should draw an axis somewhere. plus I should say minus some shifted one. Maybe I'll draw this axis on the other side now. And now this sum of these sigmoid activation functions sort of looks like a bump. OK? And this sort of tells you why it works, because bumps have compact support, at least in the limit they do, but it suffices to prove the point. So the bumps, so this function in this limit is sort of some sum of appropriate bumps where the w's and b's can be adjusted. And this theorem is a theorem that there exists some w's and b's somewhere that can approximate any function. So if I give you a sine, right, well, I could just have my neural network be a bunch of bumps, right? And the bumps are approximating the sine. And the point is, it's approximating the sine with some error, right? But as I demand lower and lower error, making that epsilon smaller and smaller, well, I just let myself have more bumps. I make the network bigger. And I can do better and better and better on this. So this is Cybenko's picture of why the universal, he proved it, right? But this is the picture of why it works, because the nonlinear activation functions can conspire together to give nice little things with compact support, and then you can take combinations of them such that they approximate anything. OK? Yes?
So yeah, we did something like this as an example in another lecture.
Great.
I have a question. What if the domain of our x values for this sine wave is infinite? Like, what if we have to approximate an entire sine wave?
Good. The assumption of this theorem took a compact space.
Okay.
So notice
K.
Yeah, I forgot to say that. K is I said it. I think I didn't write it. K is compact on RD. I should also emphasize that, like, if you go to the Wikipedia page, there's a million different versions of the universal approximation theorems under different assumptions. Probably someone generalized it, but this classic setting is a compact case. Yeah? Say one more time.
Is it possible to make a neural network that approximates a function that is non-continuous everywhere?
The question is if it's possible to have a neural network approximate functions that are not continuous everywhere. That sounds like a very sick function.
You can feed such a function into a computer.
I mean, I guess not a finite neural network. I mean, if you had like just points all over the place on R and none of them were connected to each other, you could like put bumps at every little spot, but then you would need as many bumps as there are points in R. It's not any kind of practical neural network. Yeah. Yes? Yeah. Sorry, you're asking, can you?
Yeah.
Yeah, I mean, literally at the divergent point is when the error will get particularly bad. Maybe it has to be continuous and bounded. I don't know. Because if you started doing this bump thing and going closer and closer to the divergence, there's going to be some very large error at the singular point. You probably need a continuous and bounded. But I urge you that I'm teaching you this for the sake of pedagogy, but I certainly am not familiar with the full breadth of what's out there about universal approximation theorems. And it's really an extensive literature. This is just the first result, and this is the picture of why it works. Yep. Okay. Something that I should emphasize. This theorem guarantees you that this crazy, pretty simple neural network can approximate any function under appropriate assumptions. This is where we're being physicists and not worrying about mathematical pathologies. And that means that there are w's and b's for which that is true. That does not tell you, that guarantees existence. Existence doesn't tell you how to find those w's and b's, right? So somewhere in the parameter space, there's a really good neural network. And it's a dynamical question about whether, given some random initialization over here, there's some dynamics that can actually lead you there. So we actually need to train our neural network. So this is a guarantee about existence, not about dynamics that guarantees that you can find the good point. Yeah?
Is there anyone found the theorem about that relates epsilon to the size of weights you need double?
Yeah, I forget. There are results like that. I forget the details. The question is there some sense of how big the network has to be given epsilon? Typically, you know that you need larger and larger n, so the error in the supremum goes something like 1 over n to some power. There are versions of that story.
How do you know it doesn't grow faster than that?
Or
is it known?
I think it's known. I just don't know the details of the result.
Okay.
Yeah. Definitely the picture is that as you take the infinite width limit, n is called the width. As you take the infinite width limit, the error that's achievable gets smaller and smaller. So in some sense, the error goes as 1 over n.
Okay.
Good. OK. Very good. So that's Cybenko universal approximation theorem. I did my boards out of order. I failed. But that's fine. I have one more theorem I want to tell you. I gave you the caveat. Existence of a neural network that's good does not mean that you can find it. Good. One way that you know that is because this theorem's from 1989, and neural networks were a less studied subject until 2012 when people got really good at training them. So the dynamics became tractable even though existence was guaranteed. OK. Finally, I want to tell you about something called the Kolmogorov-Arnold representation theorem. And I think these are the last theorems of the lectures. I'm a guy that tends to like calculations more than theorems, but I'm giving you theorems. This representation theorem is of this form. So this was one answer to the question, how powerful is a neural network? But you could have just said, this is just some result from approximation theory. Can I go find other results from approximation theory and use them to motivate neural network architectures? So now I will let f from 0, 1 to n be an arbitrary, continuous, multivariate function. OK? Then it has a representation of this form, which is that f of x1 through xn is equal to sum q equals 0 to 2n, some other function phi q, acting on sum p equals 1 to n, phi q p of xp. OK. And maybe I will push this up. I will say the theorem one more time. So I have 0, 1 to the n. I have a function on it. It's a function in n variables. A motto here, there's this, OK, the paper that led to GPT is something called an attention mechanism. And there's this famous paper that's called attention is all you need. This theorem basically says univariate functions and addition are all you need. OK. So this is a representation theorem about you can represent functions in this way. And it seems crazy, because like a counterexample that might come to mind is like, what about x times y? That's not addition, right? X times y is e to the log x plus log y. So I took my two variables, x and y, I shoved them through univariate functions called log. I took the sum, and I threw them into an exponential. So multivariate functions can have many Kolmogorov-Arnold representations, but that's one of them for x times y. OK. So this is a theorem, and some friends and I put out a paper 2 months ago that used this theorem to motivate new neural network architectures. I would point out that this function here, which is an analog of an activation function here, it goes between q and p. So if you know a little bit about neural network architectures, activations normally live on the nodes. This is something that lives on the edges. So in these types of networks, this representation theorem motivates architectures where the activations live on the edges. I think that's, is there any other comments I wanted to say there? Hold on. Yeah, OK. I was going to draw a picture, but it's actually not crucial. So I'd rather take questions for the last 5 minutes to try to clarify anything. Does anyone? Rakab.
So are these phis, like, are they guaranteed to be like nice functions that tend to be really weird, non-continuous things?
Good. So they can be very funny functions. Yes, the question is, can the phis be weird?
Especially if f is nice.
I think there are cases where f is nice and the phis are weird, which is part of the reason there was some work on this idea in the neural network architecture community about why this would not be a great idea for a while. And part of it had to do with the phis being weird under certain circumstances. But this theorem has, so n is the input dimension. And so this like maps you to an n-dimensional layer, and then a 2n plus 1-dimensional layer, and then to a scalar. There's some shackles in this theorem that if you're strictly following it, you have to follow. But you could say, we're doing ML, let's be empirical about it. Let's just say this thing motivates arbitrary widths. You could stack this thing and turn it into a deep Kolmogorov-Arnold network. And part of the way that we sort of made progress was to let ourselves be motivated by this theorem, but to write down a more general thing that's motivated by it, even if the theorem doesn't back it up. And the reason that's relevant, so for example, if f of x1, x2, x3, x4, what did we do? X1 squared, x2 squared, those are univariate functions, right? So I take my univariate functions, I add them. I'm going to throw them through a sine. I'm going to add them after throwing them through a sine, and then I'm going to exponentiate. So that's a function. OK, fine. The point is that this function, when I write it that way, that function doesn't fit that form because in some sense, there's 3 sets of univariate functions. There's square, and there's sine, and there's exp. So this thing naturally would be like a 3-layer version of that thing, but the theorem really only guarantees you 2. So we tried to come up with, we just naturally came up with a generalization of the theorem that allows us to represent this as a 3-layer thing. Even though there's not theorems to back it up, you can just train it and see how it does. But just to summarize, and then I'll really take questions and be done. I'm done talking about expressivity. I'm going to talk about statistics and dynamics. But part of the point is that neural networks are powerful. And there are points in their parameter spaces that can basically realize any arbitrary function. And there's probably a lot more results in the approximation theory literature to pull out to be able to motivate new architectures. But they're powerful. And then once they're powerful, we have to talk about the statistics and the dynamics. And that's what we'll do. Yeah?
So this is, again, only about existence. Can you actually find these functions phi? Do you have an algorithm to find phi?
Good. Both of these are existence theorems. And then what you do in practice is you write down these sorts of structures on a computer, and there's parameters appearing in them, and then you update the parameters to try to find the good representative. And yeah, I mean, it can be done. That's sort of the punchline, is that for a long time, there were these theorems that backed up why neural networks were a good idea, if only you could find the parameters. And what's happened in the last 10 years is that we've gotten a lot better at finding the parameters, at the dynamical question of how do I start over here and go to the good representative. And that can be done in both cases.
But not analytically. It's
not.
So you can't take that one and analytically write it as only 2 layers from something.
I mean, I could analytically. I mean, I did just write that analytically as a 3-layer thing. There is a 2-layer version that you could try to find via regression by parameterizing the network in some way and then doing regression. But
the promise here is that you can always find the 2-layer version, right? No matter how complicated.
The promise here is that there's a 2-layer version, but I would say that we're not using that promise. What we're saying is that this is a good idea regardless of the 2-layer version. And some functions might more naturally admit a representation in terms of more layers or higher width. And I think that's the thing that was really novel about the paper, is that we went to depth and width that was not allowed by the theorem, just saying, I mean, mathematicians often prove things under very specific circumstances, and the ideas are often better than the limited circumstances in which they were able to prove the theorem, right? So we're being physicists. We're not worried about whether the theorem applies. We take their idea and we empirically try to find good functions of this form. Yeah. Anyone else? I'll take a sip in case stuff comes up. Questions about any of it?
keep taking identity maps with more layers. Doesn't alter the computing.
That is true. You could do identity maps all the way, I guess, and then or zero maps. Yeah. Okay, fair enough. I mean, in practice, we find that the things that are found dynamically are not lots of identity and zero maps. And in particular, in this case, the 3-layer thing, none of those are identities or zero maps. They're x been signed and squared.
Well, the follow-up question is, when you study this sort of maps, you find the 3 layers. Do you find what happens with the 4-layer or deeper?
Yeah, yes. So the question is, did you try a bunch of different things for a fixed function? And the answer is yes. So like, there's a natural 3-layer thing you would write down associated with this. But you might ask the question, can I take a big one of these networks and then train it on this function and hope that it's going to find a subnetwork that accurately represents it? And the answer to that is yes, but sometimes it finds something that is not the thing that humans would write down. So the dynamics can lead to a different architecture, a different topology for that function than humans would naturally write down. And sometimes that learned thing does better. So there's a question of whether you should put in the human bias or just start with a big one and let it learn. And in some cases, we found that it learned better on its own. A couple of you this morning said you wanted me to talk specifically about this result. This is all I'm going to say about it in these lectures. Definitely bother me after about it. OK, I'm over time. Tomorrow we'll start with statistics, and then we'll go to dynamics. And then with whatever time's left, I'll talk about field theory perspectives on these things. Thanks a lot.